Hi there. Hi there. Welcome back to the channel. In this video, we're going to be talking about image formation on curved mirrors. Now, you see, this is going to be, I'm going to discuss this also when we'll be talking about waves. It's going to be part of our wave series, but I'm releasing this video first because some students have been demanding for it. So, but do well to watch this video from beginning to the end because it is going to really teach you how to by yourself understand the images formed on plain mirror without having to cram them from textbooks, the characteristics of those images, without having to cram them. You understand how to by yourself come up with the answers. All right. So now, first, let's talk about what's the difference between a curved mirror and a plain mirror. So we have plain mirrors and we have curved mirrors. So we have plane mirror because the axis of symmetry is parallel to that of the image of the object itself. So we know we have object and we have image. So what is formed on the mirror is the image, and what you put to the what is placed in front of the mirror is the object. And you know the mirror is a reflective surface, so it operates by the principle of reflection, isn't it? So when ray of light, your image is formed when ray of light that is incident on the object strikes that mirror and is reflected back. Is that okay? So that is how we form our image on the mirror. Now, for a plane mirror, we have that since the axis of symmetry is also parallel to that of the image, we're going to have that the distance of, if this is our object, the distance, u, will be equal to the distance of the image that is also formed. Is that okay? The distance between this and the mirror, so it's quoted at the back. So the distance between this object and the mirror is going to be the distance between the image and the mirror. They are going to have the same height, meaning that the image that is formed will not be magnified or diminished to be the same size as the object. This is going to be laterally inverted. This is going to be the lateral inversion of this. Lateral inversion simply means the opposite. So if you want to test that, if you look at this word, for example, in a mirror, let me use a simple word. For example, so if you look at this word in a mirror, it's going to show you pun, pun, a play upon words. So you see, this is a lateral. So if I put mirror here and I look at view this word, I'm going to see pun, pun, and that is lateral inversion. So what the mirror does, what a plane mirror does, is it produces a non-superimposable image of this form. Is that okay? So non-superimposable means like our palms are mirror images of each other because they are non-superimposable. Now, if I impose this hand on this hand, I don't get. They are not equal. They don't stand. They don't stay the same as when I put it this way. Do you understand? So they are not superimposable because they are mirror images. So this hand on this hand, when it's looking at this hand, when it's facing this hand, they are equal. They are the same. So those are mirror images. So and it's because of lateral inversion. All right. So that's how lateral inversion works. All right. So and then there is also the fact that we talked about the height, the distance, the image is formed behind the mirror, the image that is on the plane mirror is formed behind the mirror. Now, you see, these are and the image is erect. The image is erect. Is that okay? So these are the properties we are going to be observing in the images formed when we use a curved mirror. Now, there are two types of curved mirrors. We have the concave mirror and we have the convex mirror. We have the concave, as I said, the concave mirror. So we have the concave and the convex. So in this case, the concave is the one that's going to have many diagrams because the images the images formed are position based. Do you understand? So now, what is a concave mirror? Concave mirror, you can draw it this way or this way. Just make sure that the part that is quoted is the back curvature. So if I quote this point, it means this to be the front of the mirror. This point is the front of the mirror. This point is the front of the mirror. Making sure that I quote this part. So that is a concave mirror. Either way you want to draw it. But I prefer to draw this. So another name for a concave mirror is this. Another name for a concave mirror is, now looking at this, what do you see is doing? It's converging, isn't it? It looks like it's converging, like it's closing in on something. So it's going to be called a converging mirror. While this will be called a diverging mirror. It's a diverging mirror, that's a convex mirror. And another thing is that this, for lens, the concave lens will be the diverging lens. And it's very simple. This is a concave lens. This is a concave lens. So it's going to be a diverging lens. While the convex lens is going to be the convex lens will be a converging lens. A converging lens. Is that okay? It's going to converge. All right. So that is that for concave and convex lenses. Now, in order to form images on a mirror, the following rules are important to be the following rules should be noted in order to know the image formed on a concave mirror. We have the rules. The number one rule is this: that the how was the exam? Okay. Just bring out is your last one. What do you have tomorrow? All right. Bring out your PVs. All right. So the first rule is this. The first rule is this. The first rule is that the ray of light that is incident, that is parallel to the principal axis. Okay, no. Before we learn the rule, we have to actually learn the properties. So for this particular convex mirror, this line here that passes through the center of this mirror is called the principal axis. This line is called what? The principal axis. Principal axis. And the radius, now you see, if you look at this, this is a form of an hyperbola, right? Which is a part of a sphere. So the radius that gives rise to this sphere is going to be, for this concave mirror, is going to be called the center of curvature. So the center of curvature is equal to the radius of the sphere that gave rise, from which this concave mirror arises. So the sphere, if you are drawing it, it's going to be, there's a radius with which that thing is drawn. So that radius is going to be the center of curvature. And there is this, the midpoint between the center of curvature and the center of the mirror. The center of the mirror is called the pole. The center of the mirror is called the pole, represented by P. And C is the center of curvature. Center of curvature. In lenses, we are going to be calling them radius of curvature. Here is center of curvature, and this place, the midpoint between the F, the center of curvature, and the P, which is the pole, is called the focus. The focus. So the focus is the midway between center of curvature and the pole. All right. So let's now talk about the rules quickly. So the first rule says that a ray of light that is parallel to the principal axis. Now, follow me through as I go, and make sure you are not missing any part, because these rules are very important. So the ray of light that is parallel to the principal axis. So if a ray of light is parallel to this principal axis, once it strikes the mirror as the incident ray, by the time it will be reflected through the focus. So if the ray of light is parallel to principal axis, it will be reflected through the focus. So let me show you what that means. So if I have my concave mirror like this, and a ray of light is drawn such that is parallel to this principal axis. By the time it will be reflected, if this was our center of curvature and this is P, this is the focus, by the time it will be coming back, by the time it will be reflected, this is our incident ray, by the time it will be reflected, it will be reflected through the focus. And that is how this guy, concave mirror, converges the ray. That is the concave mirror actually converging the ray. So we said the ray of light, by the time it touches here, it's going to what? Passing through the center of, passing through the principal, the focus. Or you call it principal focus also, center of curvature, principal focus. If the ray of light you take passes, is parallel to the principal axis, make sure that it passes through the center of curvature. That's just the rule. The second rule is just the opposite of that. And what that second rule says is that if your ray of light is now passing through the focus as the incident, that is, if the incident ray is passing through the focus, the opposite is that it's going to be what? By the time it will be reflected, it will be reflected in a direction that is parallel to the what? To the principal axis. And let me show us that using this guy. So if you draw a ray of light to pass through the focus from the beginning, so if the incident ray is actually passing through the focus, by the time it will be reflected, it will be reflected like this. Or you can draw it this way, such that your ray is coming from underneath as far as it is passing the focus from the beginning. Once it's passing the focus from the beginning, it's going to be reflected off in this direction. And what did you see? It is just the direct opposite of this. Is that okay? And that is so because of what is called principle of reversibility. The principle of reversibility of light. And it's that principle that makes us to say that if light is incident on a plane surface, this being our normal, the incident ray, is that principle of reversibility that makes this rule to stand. The rule that says that this angle of incidence is equal to the angle of reflection. So either way, if I invert this thing, I see have what? Angle of incidence what? Equal to angle of reflection. So what does that mean? The principle of reversibility holds such that when a ray of light passes through the focus, it's reflected at an angle that is parallel to the principal focus, and if it's incident at an angle that is parallel to the principal focus, to pass through that if it is parallel to the principal axis, it will be reflected through the principal focus. So that is the first rule, and this is the second rule. That is just an inversion of this, that the ray of light that is now passing through the principal focus will be reflected parallel to the principal axis. So that is the second rule. Now let's take the third rule. Now note that for each image you are going to be drawing, for each diagram that you are going to be producing, you are going to use at least two of those rules. Now, the third rule is the one that says, if a ray of light passes through the center of curvature, if it passes through center of curvature, it will be reflected back along the same path. That is, it will be undeviated. It means that it will, if a ray of light, so let's draw it. So I have my center of curvature here, for example. I have my focus here and my pole here. So if a ray of light, you draw a ray of light to pass through the center of curvature, by the time it will be reflected, back along the same path. And this is so because of this. If you remember in plane mirror, that since the angle of, if, for example, we said that the angle of incidence will be equal to the angle of reflection. If the angle of incidence is equal to, what if the ray of light were to be reflected, to be incident normally? If the ray of light was incident normally, it means by the time it will be reflected what? Normally also. So the reason why this is the case is because the ray of light, when it passes through the center of curvature, that center of curvature is normal. It means the reason why it is going back along the same path is because it is incident normally. So a ray of light passing through the center of curvature is incident normally on the on the plane of the mirror. It is incident normally on the plane of the mirror, and I hope that is clear. It is incident normally on the plane of the mirror. So, and then the that is the rule. So either ways you go is that you can also go like this, that the ray of light as long as it is passing through the center of curvature, no therefore surely that it go back along the same path. So, and that is so because we said it is incident normal. So that is normal incidence. Because of normal incidence. And we say it is normal incidence because the center of curvature is the normal, the line of normal of that part of the center of curvature is the normal to the curve, to the plane that is the plane of that curve. That is the normal to the plane of that curve. Then the last rule, there are 4 rules. Now this last rule, you should rarely or never even use it. This is because of the trickiness of the rule. You cannot exactly draw it, and I'll explain in detail. Let me first talk about the rule. The rule says that if a ray of light passes through the pole, it is going to be reflected at the same angle. It's going to be reflected at the same angle at which it is incident on the pole. So, for example, what it's saying is this. This is my plane mirror. So, if I have a ray of light to be incident on my pole, this way, this is my pole, my focus, and my center of curvature. So, if I have a ray of light that is incident here, like this, at this angle, by the time to be reflected, you didn't go and call this boy. When did he tell you? Okay. So if by the time to be reflected, you didn't tell me yesterday. If a ray of light is incident at this particular angle I, by the time to be reflected, it will be reflected at angle R, which will be exactly equal to the angle I, at which it was incident on that pole. Do you understand? All right. And what this is saying is basically that the reason why it is like that is that the reason why I said you can't use it first is that you cannot exactly determine the angle because, for example, in a plane mirror, you can use this plane as a straight line on which you can determine the angle at which it is incident and the angle at which it is reflected. But for this one, because it's a curve, there is a plane here, actually. So you cannot exactly say the direction of the plane because the plane might not be the plane along which, it's a tangent. You understand? This line is going to be a tangent. This line is going to be a tangent to this curve. This line here, this plane is going to be a tangent to this curve. So you cannot say exactly at what angle at which it is touching this line. So you shouldn't use it because of accuracy purposes. All right. So, and that is that. So, and all right, so those are the 4 rules, but except where you can actually, because of maybe, for example, for those of you that might be using a graph, so you can use a graph to determine your plane, and then you can easily find out your angle by yourself. Then you can use this rule, but otherwise, you should use only either of the 3 rules that we have talked about. All right, let's now go to finding our images by drawing out. Using these rules by drawing out the possible images that could be formed. So the first one is the first condition we might have. So the conditions. The first condition we might have is if we place our image at beyond C. So if any image is placed at the beyond C, that is farther away from C. So I will have my curved mirror like this, which is my concave. Notice I'm quoting that back. So if my C is here, and my F is here, and my pole is here, notice for you are going to be using a ruler. So when you be drawing it, draw a particular, for example, you can take about 10 centimeters for your pole. So use your Give me your, did it come with your asset? Okay. So if you have, since you'll be drawing with a compass, so take your compass and measure on your ruler, measure, if you want to use any convenient centimeter, so I could use, for example, 12 centimeter, 10 centimeter. So measure 10 centimeter and draw your curve, your arc. So when you draw your arc, that point, which is the radius that produced that arc, is going to be your center of curvature. The midway between it, so if you are using 12 centimeters, it means at point 6, you mark your focus. Is that okay? So that's how to produce it. Now you now place your object at beyond C. So the first condition is the condition where we have our object at beyond C. So we can use any of the rule. Let's use the first rule that say a ray of light that is incident on this is going to be, by the time it reflected, along, passing through the focus. So a ray of light that is incident. Now my own is not so straight, so but you are going to be using a ruler. So but try as much as possible, make sure it's parallel to this. Then by the time you be making it to reflect, it's going to reflect through the focus this way. So this is reflection. So what does that? That's the first rule. Now let's use the second rule. The second rule says that if the ray of light, you can use any other rule. You can use even the third rule, but I want to use the second rule, which is the reverse of this. The one that says that if the ray, you make the ray to pass, you know you are the one controlling this. So you want the ray to actually pass through the focus. So if the ray passes through the focus, if the ray passes through the focus, how will it be reflected? It will be reflected through in a direction that is parallel to this principal focus, right? Principal axis rather. So in this direction like this. So it is almost parallel. So notice, so this is the reflected ray for this other one. So notice our image is always formed where the two reflected rays meet. Our image is going to be formed where what? The two reflected rays meet. So look at our first reflected ray and look at the second reflected ray. We can even label them. So this is our second reflected ray. Where do they meet? They meet at this point. So our image will be formed. Which image? The image of this head. So our head is going to be here. And then it means that the remaining body will just draw it to the plane, to the principal axis. So what are the characteristics of this image as you are seeing here? The characteristics are, number one is upside down, right? So it is inverted. It is inverted. Number two, now there are two properties that always work together. If your image is real, it's almost always going to be inverted. So we have real and inverted image, and then we have upright and virtual. So if your image is virtual, it's usually upright, or it's almost always upright. Do you understand? So we have real and inverted image, and what? Virtual and upright image. So those two rules work together. So once you see that your image is inverted, know that it is what? It is what? A real image. And what is a real image? A real image simply means that if I put a photographic plate along the path of that reflected ray, it's going to form my image for me. It's going to form a picture. We're going to have a picture. Is that okay? So and that is the principle of operation of even a pinhole camera. It creates an inverted image, an inverted and real image. That is why you have the image casted on that photographic plate. So that is what a real image is. Why a virtual image will not form any image on a photographic. All right. So that's the first thing. What did you notice about the size? The size is smaller, isn't it? Look at this size here, and look at this. The size has been reduced, right? So the image is what? Is diminished. The image is diminished. So what? Check. Is this the record? Check. You see it right? Okay. So the image is diminished. It means that the size is smaller. So when you place your image beyond C, your object beyond C, the image formed is always smaller. Then another thing is that the image is going to be formed between C and F. That's the position. Let's also talk about the position. The image will be formed between C and F, and it's always the case. In as much as you drew the entire thing accurately, you produce your images, your rays accurately, you are going to form your image between C and F. So that is basically, in fact, these are the 4 major points that are needed for your exam. These are the 4 major points. And you also notice that the object distance, the image distance is shorter than the what? Than the object distance. Image distance is shorter than the object distance. Image distance, image distance, that is V shorter than U, that's the object distance. All right, so I mean those 5 are very okay as your characteristics. So these are the X6 of the image that were formed. Now let's go to the second condition. So the second condition is if we were to place our image at C, for example, so any place beyond C, we're going to have all these characteristics. What if we now place our image at C? So what if we place our image at C? Let's place our image at C. If we place our image at C, we're going to have this. So if this is our F, this would be C. This would be C, our F. Making sure that the F is just the midway between C and P. Is that okay? Our focus is midway between center of curvature and P. So let's say we place our image at C here. What is going to happen now? Also recall that it is possible that we use this other rule that says that we should make an image, a ray to pass through the center of curvature. If we make our ray to pass through center of curvature like this, what do you see? It's going to be reflected back along the same path. Notice they are meeting almost at the same point. Is that okay? So that's just to validate the fact that any tool you use, you get the same answer. You get the same answer. All right. So let's use the first rule also and the second rule. The first rule says that our ray of light that is parallel to this principal axis. So this is not parallel. Let's make it parallel to the principal axis. Okay. So it's going to be reflected along the center of curvature. Along the center of curvature this way. All right. So that's reflected along the center of, along the focus rather, the principal focus. So this incidence, this reflection. When the ray of light is now passing through focus, if we make our incident to pass through focus, by the time it will be reflected, it's going to be reflected parallel to the principal axis. Parallel to the principal axis. Okay. This is not so accurate, but if you notice, it is very close. It's very close to our center of curvature. So if you will be drawing your own, you will notice at the end of the day that when your ray is placed at C, your image is placed at C, it's going to form exactly on C, provided your diagram is accurate. Now, if you look at my curve, in fact, my curve is not so accurate, and that is one of the reasons why the diagram is not accurate. Let me try to make this a little more straight. We'll have something like this. Then by the time to be reflected along, so this one is coming from here. So by the time to be reflected to be around here. Either way, it's not on C, but by the time you draw your own, you are going to make sure that it is going to be on C because of the fact that when an image is placed, an object is placed at C, the image formed will also appear at C, and it will be inverted. And look at the characteristics. Notice the size. The size is almost equal. So what does that tell you? The image will first be inverted. So if it's inverted, it will be real, isn't it? It will be real. But how about the size? The size will be the same. So notice the image I formed. The object from this image, and it's almost the same. It's almost the same. So if this thing were to be an accurate diagram, it should actually give you the same size. It should give you the same size, right? So the other thing is the position of the image. The position is going to be what? Be formed at C. So if you place your object at C, your image will be formed at C. Then, how about the distance? The distance, V, will be equal to what? Will be U. Our image distance will be equal to our object distance. Do you have any question so far? Be marking them. Mark them. Do you understand? All right. So that is the condition of image placed at C. How about the other one? The third one. What if we place our object at between C and F? So let's say we were to move it further. So we want to move our object further. So these are objects. If these are C, it means this will be F, and this will be P. So if we move our object to come here, if our object is here, what would be the case? So the first condition is, the first rule is to make our ray strike this guy in a direction that is parallel to the principal axis, and make sure that it passes, when it's going back, it should pass through the center of curvature, the principal focus, okay, like this. All right. So then the other rule now says that if it is coming through the focus, if it is incident through the focus, by the time it will be reflected, this is our mirror, the back of our mirror. By the time it will be reflected in the direction that is parallel to the principal axis. So we're going to have this. All right, we're going to have that. So in fact, this is almost very good. So we're going to have this will be our image, because the ray is coming from the head. So that's why I was talking about your ray must be at least 2, because your image will be formed by the intersection of your real intersection of your ray. So they have to be 2 rays. So that's why we're using 2 rays. And then because it's coming from the head, it's also going to form the head. If it was coming from the leg, it will form the leg on our focus, on our principal axis. So head is here. It means I will just extend the remaining part of the body to that place. So what did you notice? The first thing is this. The image is also what? Inverted. So what is that showing you? It means that so far we've been having what? Inverted, real and real, because since it's inverted, it's also going to be real. So what does that mean? It means that a concave mirror always forms a what? A real and an inverted image. A concave mirror always forms what? A real and an inverted image. How about the size? Now notice this. Look at the size of this one and look at the size of this one. What does that mean? It means it is bigger, right? So it is magnified. We say it is magnified. We say the image is what? Magnified. Is it showing that? No. So the image that is formed is magnified. Why? It is bigger than the object. The image is bigger than the object. All right. What else? How about the position? Now the position is, it is at beyond C. It is formed beyond C. The image is formed beyond C, and also the distance now, the image distance, which is V, is greater than object distance. Image distance is greater than object distance. Here, image distance is less than object distance. So we said the image is magnified. So that is the case for images that, and for an object that is placed between C and F. How about an object that is now placed? What if I place our object now at F? So we are moving it closer to the mirror. We are taking it to F now, before condition. We will place our object at F. So this one is between C and F. So if we now place it at F, what will be the case? So this is our mirror. This is our mirror. All right. It's almost turning, oh, sorry. It's almost turning into a parabolic mirror. Let me draw it again. So we're going to have something like this. Now, take note of the fact that for a parabolic mirror, the condition is almost the same, only that it is a parabola. So the curvature is more than that of the hyperbola we have here. So we said So this place will be our C, for example. This will be our F, and this will be the P. C being between C and P, around here. Okay. So what if we place our object, our guy, at F, exactly at F? What would be the case? So the first rule is very important. You see, we are using it almost all the time. So it's parallel to the principal focus. If it's parallel to the principal focus, what will be the result? It will pass through the focus, right? It's parallel to the principal axis. By the time to be reflecting, to reflect it off through the principal focus. All right? The second condition is we could make it to, now this is to your biome. You can use your discretion. Now you can now use, let's try to use the fourth rule that I said we should avoid. I'm also going to use another result, okay, to just to validate it. So, no, let's first use the third rule. Let's use the third rule because here we cannot make it to pass through the focus. So let's use the third rule that says if it passes through the center of curvature. So if our ray were to be passing through the center of curvature, and look at the way I'm going to draw it. Do you see that? I made sure that it is going to pass through the center of curvature and go straight. So if it passes through the center of curvature, it's going to be reflected along the same path. So what do you notice? What do you notice about the rays that you have? They are parallel, right? They are never meeting. Look at this. Let me try the third rule. If it touches, goes through the pole, it's going to be reflected around this direction. So that you make sure that this theta here will be equal to this theta. So one is almost equal, right? Looks like this one is a little wider. So something like this. So you see, because of accuracy purpose, that's why we always avoid that fourth rule. But notice that is what almost the same thing, right? That is happening here. There's no divergence or a convergence. What you see here is a parallel, right? A parallel beam, right? That'll be parallel beam. So what is going to be the case? The case as it is that it's going to be inverted also from what you are saying because it's going to be formed on the other side. So since it's formed on this other side, the image is going to be inverted. And since it is inverted, it's most likely going to be what? A real image. And since it is like that, from what you are seeing, it's going to take long or forever before it meets, right? So what does that mean? It's going to be what? Magnified. The image is going to be magnified. And the other thing is, the position where to be formed will where? To be at infinity. To be formed at infinity. So that image is going to be formed at infinity. Why? Because a parallel beam. And where does parallel image meet? They don't meet. They meet at infinity. Is that okay? All right. Infinity at never ending. Do you understand? So V, which is the position, the size or the distance now. You know, in fact, the V is going to be very, very greater than what? Than U again. Do you understand? All right. So that's the case for an image that is an object that is placed at F. All right. Let's now look at the last condition, which is where we now place the image between F and P. What if we place our image between F and P? Our object, rather, between F and P. Are you sleeping? Don't sleep. So what if we place our image between F and P? This will be the last condition, number 5. That's 38 minutes. I hope you're not sleeping. All right. So if we place our image at between F and P. So we're going to have our mirror this way. And then this C, this is F, and this is P. It's usually hard for me to determine the F because I'm just trying to eyeball it. So, well, you will be using an accurate scale. So you should try on all of this by yourself to know how to really draw it. So this is the back of our mirror. Now, a ray of light that is incident parallel to the principal axis is going to go out through the focus, isn't it? Then the one that is now going to pass through this focus, center of curvature, this way. Make sure it goes through the head like this. So what did you see? The ray of light that is going through here is going to be reflected along the same path. That is the third row, remember? So if it's going like this, it's going to come through here. So what did you notice here? You notice a divergence, right? even if you were to use that avoidable rule, that rule I said we should avoid, by the time it's reflected, this theta must be around something like this. No, something like this. So for the theta to be equal, so what do you notice? You notice a divergence still, right? A divergence. What does it mean? So we now produce what is called virtual rays. Let's produce virtual rays to the back. So these all the rays we have been drawing so far that are in front of the mirror, they have been real rays. They have been real rays. So you now produce virtual rays. So the rays are going to meet at the back. So and that's where our image will be formed. So what do you notice about this image? What do you notice? You notice that number one, it is upright, isn't it? It is not inverted. It is upright. So if it's upright, there is virtually, it is basically what? Going to be virtual. It's going to be virtual. Is it quite okay? So it's going to be virtual. So, and if it's virtual, what else do you notice? It's also magnified, isn't it? It is magnified. And because the virtual image cannot be formed on a photographic plate, then the fourth one is that, what do we talk about? Where it is formed? It's formed behind mirror. Behind the mirror. So far we're forming in front of the mirror. And then the last one is that the size. So what do you notice about the size? It looks to me like the object distance is less than the image distance. Is that okay? So these are the characteristics of the image formed on a curved mirror. Now, if you want to understand this fully, make sure that by yourself you attempt them in the way I've said. Use a compass and produce an image with a compass. Measure a distance on your ruler. That is easy to produce your curve. Then draw at the center of that your curve, draw your principal axis. Then that position where you put the pin of your compass, of your protractor rather, that's compass rather. So that should be your center of curvature, then the midpoint between it. So if you're using the size of your compass, if it was, let's say, 10 centimeters, it means your mark, 5 centimeter mark will be your focus. Is that okay? And your pole will be just that point, the center of the mirror. And then you can create this. Then use straight rulers to create your beams. And you'll be accurate. And I promise you, by following all these rules, you're going to understand this thing fully. In the next video, I'm going to be talking about, so I'm going to link the video in the description. By the time I release it on the series of waves, make sure you follow along. It's going to be very interesting and, explanatory. You wouldn't need to cram anything. All the formulas you'll be deriving, you will know how to derive it by yourself. It's going to be fully explanatory, so make sure you don't miss out on it. Do also subscribe to the channel if you are not already, and share the video with your friend. God bless you.